Hi, welcome back to my channel, and for today's video, for the complex analysis series, we will be talking about analytic functions. For those who have been here for a very long time, thank you so much for your undying support. But if you are new to my channel, please don't forget to subscribe so that you'll be updated on a lot of videos that I'll be uploading soon. Okay, so let's start with a formal definition here. So, a function f of the complex variable z is analytic at a point z0 if it has a derivative at each point in some neighborhood of z0. So meaning to say that it follows that if f is analytic at a point z0, it must be analytic at each point in some neighborhood of z0. So we say that a function is analytic in an open set if it has a derivative everywhere in that set. So let's consider this. For example, let's say our function f of z is defined 1 over z. So if you notice, this one here is analytic at each non-zero point in the finite plane. This one here, f of z is equal to the square of the modulo of z. This is not analytic. So this is not analytic, if you notice, at any point, since its derivative exists only when it is 0 and not throughout any neighborhood. So we've shown this derivative of fz equals the square of the modulo on the previous video. So you might want to check on that. So we also have another definition here. So we consider, or we say that a function is entire, also, or shall we say an entire function is a function that is analytic at each point in the finite plane. So example, every polynomial. So every polynomial is entire. So technically, because a polynomial complex function has always a derivative. We already have shown the definition of an analytic function, but when a function f fails to be analytic at a given point z0, but is analytic at some point in every neighborhood of z0, then such z0 is called singular point or singularity of f. Okay, so let's consider, for example, our f of z equals 1 over z. So remember that this f of z is analytic at every non-zero point. So meaning to say that it fails to be analytic at when z is 0. So therefore, z equals 0 is the singular point. Let's consider another example. This f of z, this one here. Now, if you notice, we've shown this on the previous video that it doesn't have any derivative except only when z is 0. So, in this case, let's go back to the definition. If a function f fails to be analytic at a point z sub 0 but is analytic at some point in every neighborhood. But if you take a look into this, it is nowhere to be analytic. Therefore, it has no singular point. That's it. Okay, so for a given discussion, for a given function to be analytic, we have these two important notes to ponder in order for us to really understand in doing things or concepts in the idea of analytic functions. Number one, a necessary but by no means sufficient condition for a function to be analytic in a domain D is clearly the continuing of f throughout D. Number two, satisfaction of the CRE, so the Cauchy-Riemann equations, is also necessary but not sufficient. So, meaning to say that if we will be able to satisfy the Cauchy-Riemann equations, that's only necessary. So sufficiency for this, we will discuss that on a separate video. So just keep updated on my channel. Okay, so we also have remarks to remember on this concept. Number one, the derivatives of the sum and products of two functions exist wherever the functions themselves have derivatives. So meaning to say that given that you have two functions here, the f and g, provided these functions have their derivatives, then the sum and products have also derivatives. Okay, number two, if two functions are analytic in a domain D, then the sum and product are both analytic in D. And their quotient is analytic in D provided the function in the denominator does not vanish at any point in D. So, things to remember is two functions are analytic, so the product and the sum are also analytic. The quotient is also analytic provided that whatever the functions on the denominator, it should not vanish at any point. That's the message of these remarks. Okay, that's it. Okay, suppose that a function f of z, this one is analytic in D, and that the image of D under the transformation, so our transformation here is w equals f of z. This one is contained in the domain of the definition of a function g of w. So the implication is that the composition g of f of z is analytic in D. In fact, the derivative of g of f of z with respect to z, that's equal to g prime of f of z times f prime of z. That's it. Okay, now, so let's play now with examples. So let's start with having example f of z equals z cubed plus 4 all over z squared minus 3 times z squared plus 1. So if you notice, this one here is analytic. So that means the derivative exists except only when z is equivalent to plus or minus square root of 3 and plus or minus I. Why? Because if z equals plus or minus 3, then what happened? Z squared minus 3, that's equivalent to 0. And we should not take into consideration that this one here is in this value here. Also, if z equals plus or minus I, z squared plus 1 is 0. And again, we are not going to consider that this will be 0. Hence, we are actually avoiding on this. In other words, this one are singular points. That's it. Okay, so let's consider example number 2. Let's say our f of z here is cos x cos y plus I sin x sin y. Okay, so what does it mean? This one here, this implies that our component functions, that u of xy, this is equivalent to cos x cos y. Our v of xy here is sin x sin y. Okay, and the message here is that we know for a fact that this is analytic everywhere. Why? Because the derivative of this one, this cos x and cos y exist, and we should know that from our basic calculus class. And also this one here is the derivative also exists. Therefore, our f here is entire because the derivative it's analytic everywhere. That's it. Okay, we will also show an important theorem, and I would say this theorem is actually powerful in the sense that this will always come out for in the succeeding topics in complex analysis series. So we have a theorem here saying that if the f prime of z is 0 everywhere in the domain D, then f of z must be constant throughout D. That's it. We will continue with our example now. Example is, suppose our f of z here is u of xy plus I v of xy. And then f of z bar, so that's the conjugate of the function. So of course, this is u of xy minus I v of xy. Now, suppose these two here are analytic in a given domain D, then what happen is our f of z must be constant throughout the domain D. So that's the claim here for our example. Okay, so we will show this claim here. So again, if a function and its conjugate are both analytic, then that function must be constant throughout D. For convention, we write f of z to be u xy. So we will capitalize that vxy. Your uxy is our small u of xy. Vxy, that's the small vxy. Then f of z here is analytic. Then by CRE, what does it mean? U of x is equal to v of y. And u of y is equal to negative vx. That hold in D. So f bar of z, so that means the conjugate is also analytic. So this means that your ux equals vy and that uy equals negative vx. I will compare this one here, this equation here and this equation here. So if I'm gonna combine this equation star and double star, I would get ux equals negative vy and your uy equals vx. And so if I'm gonna add this one here, and so if I'm gonna add this equation here and this equation, I would get the result as u sub x equals 0 in D. V sub x is also 0 in D. So this means to say that f prime of z equals ux plus I vx. We've shown that on the previous video that the derivative is this one. And so this is 0 plus I 0. This is 0. Okay. Therefore, by the theorem we have presented earlier, this means to say that f is constant throughout D. Okay, let's consider another example. And this example is actually somehow connected with the previous one. So suppose further that f of z is constant. So the conclusion for that is f of z must also be constant. Okay, so let's show the proof on that. Suppose f of z, since this is constant, we let this by c. So that's for all z in D, and your c is in R. Now, let's evaluate this. If c is 0, what happened is, if c is 0, then your f of z is 0 everywhere in D. If c is not 0, then f of z, I can have f of z bar. So this is this one. and that's gonna be c squared. So meaning to say I square both sides of this one, and so I get this, but the square of this one is equivalent to the product of this. So note that your fz is never 0 in D. So this means to say that your f of z bar, or the conjugate, is c squared over f of z. That's for all z in D. And so meaning to say that f of z bar, or the conjugate, is analytic anywhere in D. So by example number 3, f of z must be constant throughout D. That's all. Okay, so that's all for now. Thank you so much for watching. So if you have any questions or clarification, don't hesitate to comment down there so that I would be able to improve my video and my discussion. So guys, if you have any requests, you can comment down there as well so that I can be able to discuss on that. I'll try my best. And guys, thank you and have a great day to you. Bye for now.